Hello, this is Dr. Lukes, and this is Process Control. We are going to start looking at Chapter 8 on feedback controllers. Let's look at the way that the controller functions. So if we look at our PNID for a control loop, just a little small snippet of it here, we take a measurement and that measured value is sent into a controller. We also, however, are adding a set point. SP is our set point. And what the controller does is it compares the two, and it does that by computing the error, the set point minus the measured value. And then it looks at that and makes a decision. So it bases its output, which is going to be designated P of T in our book. So it bases that output on the error, which is the set point minus the measured value. The easiest thing to do is something that's called proportional control. Now, KC is going to be the controller gain. That's how we'll designate it. The idea is that there is a proportionality constant, K sub C, so that when I multiply that times my error, well, if the error is small, it'll make a little fix, and when the error gets bigger, it'll make a bigger fix, right? That's what proportional anything would do. So proportional control is going to take some constant and multiply that times the error, and that will tell me how much I need to adjust my output, okay? So if we do it in terms of a change from the steady state, the constant value, so using deviation variables, the P of T that we see right here, P prime of T, that's my deviation variable. And most of the time in our textbooks, we're going to use controller gain, but when you're talking to people who do controls, they will often talk about it as being proportional band. Proportional band is basically the reciprocal of KC as a percent, okay? Now, there is some vocabulary that's going to be important, and that's direct acting and reverse acting. When KC is negative, the controller is called direct acting. If KC is positive, it is reverse acting. Now, okay, why those choices? Recall that the error is the set point minus the measured value. And so if my measurement is going up and I multiply by a negative Kc, I'm going to have a negative times a negative. That will be an increase to my output P. Okay? And when I have Kc as positive and I multiply by a negative change, that's going to be a decrease in my output. So therefore, negative is direct acting and positive is reverse acting. Now, the advantage of proportional control is that it's simple and logical, right? Little problem, little fix, big problem, big fix. But this can have some serious disadvantages, and the main thing is that you can end up with something called offset. Okay? Now, offset is an inherent steady state error, that it will go to a value and stay stable in that steady state, but it wasn't the value you wanted. Okay? And that can happen with proportional control. If that's not really critical to you, then this is going to be easy and it's going to be pretty simple to work with and tune. Okay? You're going to find an industry that roughly for the feedback control loops, this is going to be about 20% of what you're going to see. But that offset can be a problem. And so what's happening is you have an error that's just persistent, right? That it's, I wanted 1 and it's at 1.1 and it just stays at 1.1. That's a small error, but it's not going away. So what we do is we do integral control. Integral control is going to take the integral of the area over time. Remember, integral is the error or the area under a curve. So that's going to basically accumulate that small error over a long period of time. Now, we're going to take that and divide by tau, the integral time, or the reset time. So tau for the integral control is 1 over tau I. That's going to become our tunable parameter that I can use to adjust integral control. And so integral control is going to eliminate offset. But the problem here is the error has to happen for a long time. Okay? So the longer the error persists, the larger the action will be, the controller output. And maybe that's going to be a problem for us. Now I'm going to say integral control on its own is rarely used, okay? I've actually not seen it used. But PI control is very common. In fact, more than half of the systems are going to be PI control because it's going to take that proportional control and combine it with the integral control. So now I have 2 parameters I'm going to have to tune, but it's not going to be overly difficult, right? One is going to be a little challenge to tune or choose the value. 2 is going to be a little bit more, and they're going to kind of feed off each other. If we look at the math, I'm taking the error and multiplying it times Kc, and then I'm adding to that this integral of the error times 1 over tau I, but that's also multiplied by Kc. So therefore, changing tau I is going to perhaps change what I need Kc to be if I'm making choices for these 2 values. Now we're going to be doing these and modeling them in, say, Simulink, and that means we need to be in Laplace land. So if we take the Laplace transfer function, or Laplace transform of this to turn it into a transfer function, then we end up with k sub c times 1, okay? And then 1 over tau I, the integral is a 1 over s. Remember, an integrator is 1 over s. So it's kc times 1 plus 1 over tau I s. And if we combine those so that it looks more like a transfer function, we have something here, okay? So just combining those fractions into a single one, all right? I said that a lot of times people use the reciprocal of Kc and call it proportional band. They also will talk about something where that 1 over tau I, they're going to call it the reset. Sometimes the reset rate. It's going to have units of 1 over time. Now, the advantage here is clear. It's going to eliminate that offset we had with P only. But there's a disadvantage, okay? This may, in fact, create oscillation in a system that wasn't oscillating before. If I had just left it alone, it would have gone to a steady state, not the steady state I wanted. Now then, I'm creating oscillations. Sometimes that's not a problem, sometimes it is. Now, it won't always create oscillations, but it can. And the other problem is going to be reset windup, okay? And that is that it looks at this error, right? And it's got an error and it was accumulating over time, and so it's fixing it. But you fix it and it still remembers all that previous error. And even though you don't have much at the moment, it remembers all that error, and so it's going to keep fixing a problem that no longer exists, okay? And so that is a potential problem with PI control. Derivative control is going to be another one of those that's basically not really used on its own, but the idea is that it sees the system is going along fine and suddenly it starts to increase or starts to decrease. It sees a change in the error slope and it will react to that. So it's looking at changes in the slope of the error. It's suddenly increasing where it used to be flat. It's suddenly decreasing. And so that's going to be my derivative control, okay? And again, they'll call it the derivative or the rate, and it's 1 over tau d. So derivative control is looking at just a teeny little hint of a problem and anticipating that it's going to get worse. So what it can happen is you have a very small change in your y, right? Error is the set point minus the measured y. And you can have a very small change in the y, and it starts making corrections. That can be good, but systems tend to be noisy. If you've taken your unit ops lab course, you've seen that measurements, like especially like flow rate, tends to kind of bounce all over the place. Derivative control on its own is rarely used. And we could combine that with others. So say combining it with just the proportional control. We end up with this. Now the problem now is that when I do the transfer function, you end up with this expression here, Kc times 1 plus tau ds. And that is unfortunately non-physical. You have to have the denominator be at least the same order polynomial as the numerator. So the trick is they will, instead of tau ds, they'll build it by doing tau ds over some number times tau ds plus 1. Now that number is going to be a small little number here, okay, 0.05 to 0.2, but it makes it so you could physically build this. But again, it's pretty rare to do PD control on its own, but PID control is going to be fairly common, okay? It's about, on the order of 20% of the feedback controllers. It is going to be complicated to tune because we have the K sub C, we have the tau I, and we have the tau D. And both of the tau I and tau D are going to be multiplied by Kc, so you're going to need to tune these, and they're going to affect each other. Okay. The transfer function for this, is just the various pieces here, and you can get a common denominator. And again, the tau ds is generally built as being an alpha tau ds plus 1. So people use this because it's more stable than PI control alone, but it's more challenging to tune. Okay. So it's going to be used about, maybe 20% of the time, but it is going to be important. And almost always when you purchase a feedback controller, it is going to be a PID controller. And then you can choose to turn off any of the modes you don't wish to use. So most of our controllers will in fact be this type, but we won't use all of the modes. Okay. So that's going to wrap up this lesson. We'll come back and talk in our next lesson about some other variations on PID control and feedback control. Thank you very much for your time.